I'm going to talk about one barrier to using high fidelity simulations for engineering design. That is, how do you get a smooth response from a high fidelity simulation that is chaotic? A high fidelity simulation is much easier to become chaotic than a low fidelity simulation because the real world is chaotic. So when I have small children, and when I see my children running around with their shoelaces untied, I see the chaotic motion of their shoelaces jumping around. The real world, chaos is everywhere. And if you simulate the real world to high enough fidelity, you get chaotic simulations. And once you simulate a chaotic phenomenon, if the simulation is chaotic, this is a typical response you're going to get. So this is the objective function measuring how good your design is. And the x-axis is a design parameter. So if you want to say, okay, what is the trend of this objective function as my design parameter increases? If you just look at that, it's very hard to tell, right? And why is this? This is because in a chaotic simulation, if I change the design parameter by a little bit, okay, the definition of chaos is that if I change the design parameter or change anything a little bit, the time history of the simulation is going to become very different. I'm going to show you a little bit later on. And if my time history becomes very different after a while, then the objective function can easily become quite different. But if I can perform what I call sensitivity analysis, computing the derivative of the objective function, and I'm going to show you later on what kind of objective function I can compute derivative with. If I can compute a derivative, and I get a derivative like that, so this is a visualization of the slope I obtained from the derivative, then this tells me, although the objective function has a lot of noise, okay, but if I can compute the sensitivity of the denoised objective function, then I can see, okay, there is a minimum of the objective function around here, right? And then I can run the simulation for much longer time to pinpoint the objective function at that minimum. So this is the first mathematical research I'm going to be talking about. Okay, so the mathematical research is called the least square shadowing. So this is a new method I developed at MIT. So before the method was developed, this is before and this is after, accurate sensitivity analysis was computationally infeasible, even for a 3 degree of freedom system. So an ODE with the 3 components, the Lorentz attractor. With the method developed after a few years, we can now do sensitivity analysis with a system that is more than 30,000 degrees of freedom. And the sensitivity we get is pretty accurate. I said pretty accurate, that is because it's very, very difficult to actually compute the sensitivity as a reference without using least square shadowing. Here what we did was we computed the objective function over a range of parameters as accurate as we can. Actually, the whole calculations, because we have to get the noise down to such accurate level, it took 11 million time steps. So each one of them took 1 million time steps. And we did 11 sweeps. And we did 3 least square shadowing, independent least square shadowing calculations. Each of them only took 2,000 time steps. So this is having a sensitivity for a chaotic simulation is enormously useful. There is almost no feasible alternatives. And if we have sensitivity that enables design optimization, that is what I'm mostly excited about. You can do design with these sensitivities. I'm going to show examples later. You can do error estimation with the sensitivities. Computing sensitivity to sources of error is going to give you how much error you have in the quantity of interest. And you can do automatic meshing. If you know where the error comes from, you can refine the mesh over there. And you can do uncertainty quantification with the sensitivity, looking at how sensitive is your quantity to all the sources of uncertainty. So having sensitivity is enormously useful.